I'm going to do today is to finally kind of go back and move on and kind of explain kind of what the connection is between what I've been doing for the last few lectures. Last few lectures we've kind of gone back and we've gone on back to classical mechanics and talked about classical mechanics from this point of view that we're really emphasized thinking about Hamiltonian mechanics in terms of Lie algebras. But before, so I'll maybe say a little bit more. Start off by saying a little bit more about that, and then get started on the next part of the class, which is really to talk about quantization, to use what we've done so far and the way we've been thinking about classical mechanics to give a new point of view on what quantization is and what quantum mechanics is. But are there first of all, any questions about the Hamiltonian mechanics, Poisson brackets, any of this stuff? Okay, because if not, let me just start again. Maybe just kind of summarize a couple things about that, and also say something a little bit about language. About so one of the kind of bottom lines of this subject of what we've been doing so far is to say that if you have a function on phase space, that function, you can think of that function as being the generator of a symmetry. Or if you have a symmetry of a theory, you can ask what's the function that generates that symmetry. Or it's called the moment map. So maybe I'll say a couple words about that first. Okay, so the so the main ideas of the last few times was that when we were thinking about Hamiltonian mechanics, so you thought about Hamiltonian mechanics as being a story that's about a phase space M, and it for us it was generally going to be. It's really just going to be an even dimensional vector space, but the setup that's going on here generalizes to a more general set of manifolds, symplectic manifolds. And then what you had here was that you had functions on M with a Poisson bracket. You know, is what this is an infinite dimensional Lie algebra. This, in some sense, is the real significance of the Poisson bracket is that it turns the functions on a phase space into it's a Lie bracket on that. They become a Lie algebra. And then the interesting thing you could do is that if you had such a function, a function this, then what you could do is you could think about it in a different way. You could create something that I call XF. So, and I wanted to think of this as a vector field on here. And I wanted to think of vector field as something that it's something that if you feed it a function, it acts like a first order linear differential operator on functions. And so this is something that if you feed it a function, you're going to get another function. And I wrote out kind of a description of this in coordinates, but maybe it would be better to say that it really is just this thing. That it's really just this, that this vector, you can think of this as a vector field. But what it is, it's something that if you apply this vector field to a function, it's something that it just gives you it gives you another function, and that other function is just the Poisson bracket with F. Okay, and so you can think of this. There are a lot of different ways of thinking about what's going on here. So one way of thinking about what this is that this vector field is. This is the vector field. This is the vector field for time evolution, and with a Hamiltonian F. So if you want to, if you're doing classical mechanics is all about you're in a phase space M, and if you have some kind of initial condition at some initial time, and those are given by the points in the phase space, and then the Hamiltonian function tells you what's going to happen as you evolve in time, and the setup of Hamiltonian mechanics is that there's Hamilton's equations tell you that given a function, they just give you this vector field. This is just kind of a way of writing Hamilton's equations, and then the time evolution is just the so at each point you have a vector, and then this vector is the infinitesimal rate of it's the tangent to the trajectory through this point at time zero. So your trajectory is then going to be something that's going to be tangent to this at time zero, and the vector field is exactly the thing which tells you it's always going to be tangent to the trajectories. So this is just a way of encoding, saying that associating to a Hamiltonian function a vector field is a way of encoding Hamilton's equations. That's one way of thinking about it. But the other way of thinking about it is that okay, anyway, but you could so this is one. This is what's true. And then now the other thing that's true is that vector fields give you also give you a Lie algebra, because if you have two vector fields, you can take the commutator. You can do the first one, then the second one, and then the second one, and the first one. Take the difference, and so this gives you another. This is also a Lie algebra with a commutator of vector fields. This is a little bracket, and then this. So this map is a so this is a homomorphism of Lie algebras. So this is taking this is. Did I want to actually? Yeah. Anyway, so this takes under this map, the Poisson bracket of two functions becomes the commutator of the corresponding vector fields. So there's a huge amount of stuff about Hamiltonian mechanics is encoded in that. Okay, now and maybe I guess so. Let me actually then, so when you're thinking about this, it's probably a good idea to keep in mind a couple of examples. So let me give you these examples. So what I want to take, so if you want to take your function just to be p, so let's just do this for d is equal to 1 for a minute. And so if your function is just the coordinate p, then x of p of if you compute what this is, it's so it's here with p, and but that's just the sorry dq. I guess the sign right. Yeah. So what this is saying is that the yes. So this function becomes the vector field, which just gives you the infinitesimal trend, which is just infinitesimal translations in the q direction. So as a vector field, the vector field corresponding to p in two dimensions. If this is q, it's just it's going to be just a constant vector field that's the same thing everywhere in the q direction, and it's just as a operator on functions, it just takes the infinitesimal, just tells you the infinitesimal change in the q direction. Okay. And then the other example to keep in, the other good example to keep in mind is if is rotations. And d is equal to 3. And then the functions that you want, then associated to each for each Li element of the Lie algebra of SO3, you get a function. So Li, you get a function which I'll call the moment map for L sub I. Or else, let's say the moment map for L sub 1 is just going to be Q2 P3 minus Q3 P2. So it's and this is going to, and then the rotate then this guy. So this is going to be the vector field corresponding to. Well, let me just say this. So it's going to be whatever. E minus Q3. What it's going to be is it's going to be just a, if your L1, this corresponds to infinitesimal rotations about the x-axis. So this is going to be just d. This is going to be just d theta dot for a rotation about the one axis. And I'm not sure I've got the sign right there yet. It depends upon how I've got I've oriented this correctly. But anyway, there's a really confusing sign to keep track of. Okay, and then but the much more, I mean, the very non-trivial thing that happens here is that rotations about different directions, about different axes don't commute. So if you can, and this corresponds to the fact that the Poisson brackets of these moment map functions for the various L sub I satisfy the Lie algebra relations for SO3. But but in general, what we have is that if you've got a group G acting on your phase space and it preserves a Poisson bracket, then you're going to get it's going to correspond to a infinitesimally. It's going to give you a vector field, and that vector field acts on functions by x sub UL. And so what you'll see is that the terminology you'll see here is that mu sub L, this function, generates it's the infinitesimal L. So these functions are something that they're the thing which kind of, for if you want to know what's going to happen if you do some infinitesimal change corresponding to this symmetry transformation, it's going to change an arbitrary function by this Poisson bracket with this function. And so this function, or the so-called moment map, or whatever it's called the infinitesimal generator of the symmetry. And so this is a very nice way of thinking about what happens in Hamiltonian mechanics. And the one reason for, and the really nice thing about this is that there's a very similar story in quantum mechanics, which we'll get to kind of starting now, I guess. Okay. And you can think, yeah. And then anyway, so there's this example. I mean, another example, actually, kind of the zeroth example here is if you take your function is the Hamiltonian function, and as I said, then the vector field is just the vector field for time, giving you time evolution. Okay, so that's pretty much the summary of what I wanted to say about what I said, the point of view on Hamiltonian mechanics. Okay, so let's get back to quantum mechanics. So the history of quantum mechanics is really that simultaneously Schrödinger was doing his point of view on quantum mechanics involving the Schrödinger equation, but Heisenberg had this more kind of algebraic way of doing it, that he realized that a good way to think of this it was in terms of operators, and what he'd and he realized that these operators didn't commute, and so Heisenberg, so back to quantum. So Heisenberg kind of realized, by looking at trying to make sense of calculations involving spectra and things, that what was going on was that corresponding to your Q and P of classical mechanics, now you had in quantum mechanics you had operators which satisfied QP, which instead of commuting were had this commutation relation. The so-called Heisenberg commutation relation that Q and P is I times H bar times the identity operator. And so, and Dirac, looking at these calculations of this sort involving this, Dirac very quickly kind of realized that, wait a minute, that that this looks like that this looks. He decided, well, he realized that this reminds me very much of what I learned when I was learning about the Poisson bracket, and that this reminded him a lot of QP is equal to 1. And so what he suggested, so to kind of say what he so Dirac's idea really was that say that that to any function f on m, you should get an operator over to that, and that these operators are going to satisfy, and that if they're going to behave nicely under their commutation relations are going to be determined by what the classical Poisson brackets were, so that the operator corresponding to a Poisson bracket is given by the commutator of G. And then there's a minus I over H. Okay, now so to keep track of these these minus i's and these signs here, you want to notice just that the O F is the reason for choosing these particular operators is you want just the reason for choosing Q and P normalized that way without an I was that you wanted them to be self-adjoint. If they're self-adjoint, then they're going to have real eigenvalues. But mathematically, it turns out that it's better to if you want to think of these things the way I want to think about them in terms of coming from the Lie algebra representation, it's better to put in an I, and so we're always going to so this is let me just say this. So Dirac's conjecture is that this is the same as assuming Lie algebra representation that pi prime of f is equal to minus I of f. And then so then the Lie algebra homomorphism property is going to be that pi prime of f and g is equal to pi prime of, well, that's pi. Well, the algebra homomorphism property is going to be pi prime of f, pi prime of g. Okay. But but this is just going to be so this is just going to correspond to this, and I'll just set h bar is equal to 1 and not keep worrying about the h bars. But if you set h bar is equal to 1, then you should see that this equation, if you relate functions on phase space to operators this way, this equation here is just this equation, and it's just exactly the property that says that this association of functions to operators is just exactly the what you would get if you had a Lie algebra representation of the Lie algebra of functions on the functions where the Poisson bracket is the Lie bracket. Okay. So this is it. Okay, so that now if you this is what's often called kind of Dirac quantization, or what Dirac, or more accurately, what Dirac would like quantization to be, because we're going to see that it turns out you actually kind of can't do this for arbitrary functions. You can only do this for certain functions, and that's one of the trickiness of the subject. But the in some sense, what's behind all this is a very simple idea that if you think about classical mechanics as a story about a Lie algebra of functions on phase space, then quantum mechanics is just the statement that there's that quantum mechanics is going to give you a unitary representation of that Lie algebra. And the state space now is going to be states are going to be given by the space on which this representation is acts. Okay, so that's the grand picture. But now, how you have to actually try to actually do this. So we actually have to figure out what is pi prime, and what is there a pi that it comes from, and what are we actually doing? So can we actually do this? And this is what just the idea of doing this by just adopting. So let me call it. So what we're going to do now is, I guess, what's generally called canonical quantization. And so canonical quantization, what you do is you say that you basically say that what we're going to do is just use the Schrodinger representation in gamma S of the Heisenberg group to get this to work for the Heisenberg subalgebra. So this is of the things that are 1 QJs and PJs. So if you just take the linear functions on M with these basis elements, this gives you a sub-Lie algebra of the Lie algebra of all functions. And so canonical quantization says that that if you want to try and realize what Dirac was saying, what you should do is just look at the Stoner-Neumann theorem, and tells you that there's really only kind of one non-trivial, interesting representation of this, and that's the one you should use. And furthermore, you know, while you'd like to know what the algebra representation is on all functions, at least you could start off by knowing what it is on linear functions. And so on linear functions, you have that gamma prime. So I'll write by gamma, big gamma S, I'll mean the Schrodinger representation, and by gamma prime of S, I mean it's the algebra version. But that's the thing. This is going to take the function 1 and give you, and again, I'm setting h bar to 0. The minus I times the identity operator, and gamma prime S times Q, it's minus I times Q on P. Okay. So it's really, so what you normally take it as quantization, the thing it takes P to big P and Q to big Q. We're just multiplying by a minus I in order to make that that relationship a unitary representation, a generated unitary symmetry. To get skew adjoint things, self-adjoint things. Okay, so then now the problem is, what about higher order recurrence in QJ and PJ? So what happened? And so the problem you find is that you'd like to, the problem is that these things don't commute. So if somebody gives you a polynomial with a bunch of Q's and a bunch of P, and some number of Q's and some number of P's in one term, well, if you try and make an operator out of this relation on some higher order term, it's going to depend upon which order you, how you order the Q's and P's. Okay, so let's do, let me, yeah, okay, so this is actually true for, this is true for any D, but now let me go to D is equal to 1. And then, then you had, at the next order, you had QP, Q squared, and P squared. Don't worry about that. Okay, and so the idea was to take, was to extend, yeah. And again, and so what you want to do is you want to extend gamma S prime to quadratic functions. Well, the first, it's pretty, there's only one thing you can do. There's only one thing you can do with q squared. You can make q squared the operator q times itself. It doesn't mean there's no ordering problem, and you have to put in a minus I to make it squared. That's gonna work. And then you can do the same thing for p squared, and to get minus I. Okay. So on for this guy and this guy, there's really there's only one. There's kind of only one sensible choice. There's only one thing you can do. But now the problem is then this guy. What do you do about this guy? So remember, what we need to do is we want to find. We want to make some choice here of gamma S prime of QP, and so that it has the that you get some kind of operator, and that operator is going to have the right commutation relations with these guys to have to satisfy the Lie algebra relations of this symplectic group and d is equal to 1, which is SL2R. So that's what we have to try to figure out. And it turns out there's only no. So the problem is what is QP? Okay. And so the things you can imagine is well, maybe it's QP, but maybe it's PQ. They're not the same thing. Or you could put minus I and minus I. Okay. So what works is minus I times a half times QP plus PQ. Actually, this is there's several reasons that this is kind of the only this is the only sensible thing to do in this case. But one of them, but you can check that this actually gives you that the commutation relations of this guy with the capital P squared and the capital Q squared are exactly the commutation relations of SL2 of the generators of SL2R. Okay. So then then as of quadratic of well QP P squared Q squared. This satisfies the SL2R commutation rate. So you're done. Okay. Now there's a subtlety here though. This is something that's going to recur, later in the course, and later when we talk about the how to quantize a harmonic oscillator, we'll develop some better techniques for dealing with this. But there's something funny going on. which is facility, is how do you let me say it this way. So can you exponentiate these operators and get a unitary representation of SL2R. So what happens in the when you have a finite dimensional unitary representation of a Lie algebra, then it's just exponentiation, and it's just exponentiation of these finite dimensional matrices, and so you can always exponentiate and get a representation of the group. The problem here is that these are not these operators here are not, they're not kind of nice finite dimensional matrices. They're depending upon whether you think about your state spaces being functions of p's or functions of q's, there's some kind of combination of differentiation and multiplication operators on an infinite dimensional space, and you have to worry about can you exponentiate these? And so so you could exponentiate the problem with what happens is you can exponentiate q squared, or using in the representation where q is multiplication. So if you're in the so-called position space representation where the q operator is just multiplied by q, then exponentiating q squared is just multiplying by q squared. Exponentiating q squared is just exponentiating multiplying by the exponential of q squared, and that's easy. Or p squared, and or p. But the really tricky thing with this representation of SL2R that we're trying to build, though, is that we can't Fourier analysis. When we use Fourier analysis to turn this guy into a multiplication operator, if this guy's a multiplication operator, then the other guy is not going to be a multiplication operator. He's going to be a differentiation operator, and so we can kind of we can diagonalize one or the other and turn it into a multiplication operator, but not both. And so in the or in the position space. Well, let me just say, so if you want to figure out what it means to exponentiate p squared, you have to what you need to do is you're going to have to and you're in the representation, in the position space representation, then you're going to be exponentiating the second derivative. And so there's a question here: how do you exponentiate the second derivative? It's if you're exponentiating a first derivative, that really kind of just corresponds to that's some kind of finite shift. But if you're exponentiating a second derivative, it's much less clear what that means or how you would do that. So you're stuck with kind of a tricky problem here of how to how am I going to do this? Okay, but now so then the word yeah, okay, so let's maybe to get a good idea of kind of where what this problem looks like, you can think about not just exponentiating q squared or p squared, but think about exponentiating this, the sum of them. So let's do this. Okay, so what is okay, so what we're interested in is how do we exponentiate q squared plus p squared. And so remember that if you would, so in the algebra of SL2R, remember that I got a relationship between quadratic polynomials and 2x2 matrices. So this was, I guess I called this E minus F, and this was 0. It was this. Okay, so it's this Lie algebra element we want to exponentiate, and in the group, and so we know how to do the exponentiation of the Lie algebra. It's just the exponentiation of this matrix, and then we'll get something in SL2R in the symplectic group in 2 dimensions. But the exponentiation in the representation on this n-dimensional function space it means that we're going to be trying to you want to so exponentiate the operator corresponding to this, and which is this guy. But now let's say that we're in the position space representation. This is minus I over 2 q squared minus b squared dq squared. Okay. And so here you have this problem. Anyway, so here you can see the problem that you could using Fourier transformation, you could diagonalize this guy or you could diagonalize this guy, but not both of them. So it's very unclear. What does it mean to exponentiate that? If you want to exponentiate this operator, what's going to happen? Okay, so this is, and when I talk more about the harmonic oscillator, we'll develop some techniques that are maybe a bit more useful for this. But there's one thing that you can see what's going to happen is that consider. So instead of just let's look for some eigen let's look for eigenfunctions of this thing, and then on eigenfunctions of this, then we'll know how to exponentiate. We don't know how to exponentiate the operator in general, but we can exponentiate it on an eigenfunction. So consider the state q, which is e to the minus q squared over 2. Okay, so this is on the state space. On the state space that our operators are acting on, and here you have what happens is minus I over 2, then q squared minus b squared q squared. So you show that this is an eigenfunction, with eigenvalue minus I over 2. Okay, but then okay. So anyway, but the problem that you're going to find is that if you exponentiate this guy, so taking e to the minus f, this goes as this. So this guy, if you figure out what's going to happen with this guy as you go, goes from goes to the identity as theta goes to 2 pi. So what happens is if you take theta from 0 to 2 pi, you go around a circle of these guys, exponentiate this guy, compute what it finds. You find that you go around a circle of matrices and come back to the identity matrix. The problem is that if you do the same thing, e to the I theta gamma s prime of this guy, so the representation operator here, what happens as you go from theta to 2 pi, you're going to pick up, and then you're acting on psi q goes from 1 to minus 1 as theta goes to 2 pi. So if you go around the circle once here, the fact that this half here means that you're going to end up with an e to the I pi or a minus 1 when you get not e to the I 2 pi, but e to the I pi, a minus 1 when you go around once. So sorry, I think I've got this right. Okay. Okay. So this is we're going to find. There's going to be a better way of doing these calculations and seeing what the problem is that we're going to get to later when we do the harmonic oscillator. But you can already see the problem at this level, and let me kind of tell you then what the bottom line is. So this is this is analogous to what happens in the spin half representation when you act exponentiate the action of the SO3. Okay. So if you go back to what we were doing in the spin representation, you had the Lie algebra the algebra of SO3 was operated in the spin 1/2 representation, basically by these Pauli matrices with this half in it, and so you then had to so what you found was that if you exponentiated those matrices, you found that as you kind of tried to do rotate around through an angle of 2 pi, you picked up a minus sign. Well, it's something very similar is happening here, except what you're doing is you're instead of rotating in three-dimensional around some direction three-dimensional space here you're doing something like a rotation in the QP plane, and so you're it's not a physical rotation. It's something that's you're doing a rotation in the QP plane, and you're finding something kind of similar. That the you have this nicely out. So you have here have a nice have a true the algebra true representation of Lie SL2R, but you have a problem. You have a sign problem when you try to get to exponentiate and get a representation of SL2R. Okay, and so you need to treat this in a somewhat similar way, and you can talk about projective representations, or you can do various things, but you can define. You get a true representation of a double cover of SL2R. And this is sometimes called the metaplectic double cover. Well, that metaplectic group. Sometimes write it NP of 2R. Okay. So if you treat this problem the same way that you treated the problem of spin, the problem of the spin representation, here. So what's maybe it's better to just say what the analogy is. So the analogy is that well, the Lie SO3 is to Lie SL2R, and that there's two groups with this that are double covers of one is double cover of the other that are here that have the same Lie algebra, which is SO3 Lie and SU2, and here you've got Lie SL2R, and the double cover is the NP2R. And the analog here, you have the spin representation on C2, and here why this is much trickier is that you've got this infinite dimensional representation on so here it's this gamma S, on L2 of R. Sorry. So instead of having a nice finite dimensional representation on C2 by 2 by 2 matrices, here you've got this representation on this infinite dimensional function space, and the operators are given by these are constructed out of the multiplication and differentiation operators on this infinite dimensional space. But the other thing to say about this, one reason this is a lot more subtle also is here the existence of this double cover is kind of topological, that there's very topological reasons why there's a double cover here. Here it turns out SL2R actually has lots of covers. You can there's kind of a circle. There's a non-contractible circle in SL2R which allows you to construct covers of any order really that you want here. And there's just for some reason it's this particular double cover that occurs, and that's interesting. But anyway, so you should. So the bottom line here is that the reason for saying this analogy is that this side of it is fairly easy. We went through. You really should have understood everything exactly. Here, I'm just. The warning is that these are non-compact groups. Instead of compact groups with finite dimensional representations, they're non-compact groups with infinite dimensional representations, and the double cover is quite subtle. And I guess maybe the other kind of fact is that MP of 2R is not a matrix group. So I kind of told you at the beginning that the theory of Lie groups, pretty much all the Lie groups you would ever see are going to actually be groups of matrices. Well, here, so there's kind of one example that really occurs. That this is about the only example people ever see really of this is an example of it's a perfectly well-defined Lie group. It's got its dimension. SL2R has dimension 3. It's a three-dimensional manifold. Well, this is also a three-dimensional manifold. It's a double cover of this one, but there's no way to write it as a group of matrices of any finite dimension satisfying any particular condition. Okay. So the only anyway, so that's that. Okay. Okay. So now. Okay, so the story. Here. Okay, so this is the story of what happens if we're trying to extend our representation from a representation on linear functions, which was just this Heisenberg representation, and we originally constructed the Schrodinger representation. We've seen that we can extend it to all quadratic functions. And the only subtlety is that to get the quadratic functions we have to go to a double cover, just like we get a representation of the algebra is all well and good, but to get to the Lie group we have to go to a double cover. Okay, now what about higher? So what about higher order? So in other words, we'd like to know like what is gamma S prime of q squared p or something. Right? It should be it's going to be here minus it, but is it going to be q squared p? Is it going to be pq squared? Is it going to be q p q? It's a problem. And so what we would like to do is we'd like to find some choice like this, so that this is a homomorphism, that the relations satisfied by the operators on this side are the same as the relations satisfied by the Poisson brackets of the things here. And here, what happens is the bottom line here is that you can't do this. It won't work. And so the physicists. So this is what's called the operator ordering problem. And what they you get ambiguities. Of order, or h bar, or of order power in h bar. So it's going to turn out that the difference between any two of these choices, can be written as something involving some powers of h bar. So what the physicists typically say about this is, well, there isn't any. We actually don't know how to quantize higher order polynomials in P and Q in any kind of in any completely in any way that really would satisfy what Dirac wanted. So Dirac wanted these things to have certain relations, but we don't actually. There is no particular choice which is going to make Dirac happy. But what does happen is that you can just make any different choice, and then if you make two different choices, you're going to get different predictions or different numbers, but they're going to differ by powers of h bar. So in the classical limit, as h bar goes to 0, they're going to get small and go away. So these are kind of some extra. This is really a purely quantum ambiguity. And the mathematicians. So they're here. I've stated this. So I've stated this theorem, and it's called the Grunewald and Hove theorem, no-go theorem. And the theorem basically says that you can't do this. So you can't find such a homomorphism for or it may be better to even make sure to call it such a Lie algebra representation for larger algebras, Lie algebras, than the quadratic functions. That restricts to the one to ours on quadratic functions. Maybe so I'm trying to make a little bit more of a precise statement that says, okay, so we've kind of tried to build ourselves up, and we've got a unique thing and made something work on quadratic functions. And this theorem says you can't extend that. You can't extend this if you try and even go to cubic polynomials. There's not going to be any consistent way to treat them. So that's the theorem. And I want to, and I'm not going to say more about it. What you wanted to do is there's really only kind of one problem in the problem set that's due next week, and it really is just kind of work. It is just kind of playing around with some examples of what happens, like for cubic functions, and to kind of show that this can't possibly work, and to show that that this can't work. Okay, so let's see what else we have to. Okay, but the bottom line here is that we've got so we can use. We do know. So if our one thing that we can do is that we can unambiguously get a Lie algebra, a Lie group, get a unitary representation of any of G on H if for G at X on M with moment map quadratic polynomial. So, yeah, having this kind of quantization, if you think about what these operators are that you're creating, that they're the operators that for some kind of the algebra representation. Well, you can if you've got a symmetry group, so anyway, so if you've got any kind of symmetry group that acts on your phase space, preserving the symplectic, preserving the Poisson bracket, then our quantization method has produced quadratic operators, which which give you a unitary representation of that of this group on the state space. So you've got in this case, so then so symmetry G of M goes to unitary of G. Okay. So this is in this case, but if we found some kind of group that acted on phase space and the Poisson brackets and the moment maps were higher order polynomials, then we could possibly could be in trouble. We'd have to worry about whether we actually had a consistent way of getting a unitary representation on the state space. But this is the kind of fundamental relationship between symmetry and classical mechanics, that you've got some kind of classical mechanics, it has a mechanical system that has a symmetry, why the quantum system should have a symmetry, should have a unitary representation of that group. Okay, then maybe what I'm going to do, so that's the main thing, and then just the typical, the examples of this are just that the example. Well, anyway, let me just say this, that the examples of this are, so for instance, just look at the examples that I talked about earlier, the translations in position space correspond to the these p operators acting on here, the action of it, the SO3 of rotation action on this space turns into these operators here involving Q's and P's, which are the angular momentum operators. So here you have the mu's of Li go to the angular momentum operators. Involving operators Q and P. Okay, so let me just take the last few minutes and just tell you something very, very what other what is there kind of bit, I guess I wanted to say a bit besides, put this in more general context and say something about what is there besides canonical quantization. Okay, so this is canonical quantization, but so other methods of quantization. Well, we'll say, and the one which has become very popular in physics, and I'll maybe say something about it next semester. But one is to use Lagrangian mechanics, and here you quantize and get the by using the so-called path integral. And if you haven't seen this, I won't say more about this, but it's basically the idea is that instead of all the apparatus we've been using, you could you start with a Lagrangian function or an action functional, and then you try and do some to turn the problem of how to construct these operators and what they're doing into a problem about involving an integral. But the problem is that it's an integral, so you're integrating over an infinite dimensional space. So actually making any kind of rigorous sense of what these integrals are becomes a very difficult problem. But at least formally, you can write down some integral, which if you can make sense of it, it would actually, in some sense, give you a quantization. But the other, the reason for for not emphasizing this and for emphasizing what we're doing is that in this formalism, it's a lot harder. It's much harder to see why you have a unitary representation of a group. If you have a group of symmetries, basically what happens is that Noether's theorem tells you that there's going to be some function which is a generator of this. Which, if you went to the Hamiltonian system, to the Hamiltonian mechanics, would be the generator we were talking about. It would be the moment map, and so you get certain examples of the moment map from Noether's theorem, and then the reasons why the path integral should give you a unitary representation are very formal, and you don't really it's very unclear why these infinite dimensional integrals can actually be properly defined to make things come out to be unitary. That's great. Then maybe the last thing I say is much more. So this is the way physicists like to do this, because then you get these formal calculations that you can extend to higher dimensions and to quantum field theory. But mathematicians are also very interested in quantization, but they're interested in trying to find something which they can do really rigorously, and they're also interested typically in cases, not in the cases that physicists are interested in, but they're interested in trying to do this. So you can study. So let me say this. It's a general approach to representations, to finding representations of the groups. So it's a huge kind of subject within mathematics that, given any particular Lie group, to try to figure out, what are its representations, what are its unitary representations, what are the irreducible ones, how would you construct them? And it's a very difficult problem for general Lie groups with a lot of structure. So one way to approach it. So and this is called the orbit method. And the way the orbit method works is, you notice. So consider the G. So of a Lie group. So if you're trying to study a Lie group G, what you do is you think about the Lie algebra, and then what you often do is you notice then take its dual. So then look at the dual space, and then what you notice is that you find that the Lie bracket corresponds to a Poisson bracket. Okay. So the orbit method is based on the idea that, if we're going to think about Lie groups, then we should really think about their Lie algebras. And we should make a space, and instead of thinking about the Lie algebra, we should think about its dual space, it turns out. Because on the dual space. If you ask, what is the information that the Lie bracket on Lie G give you? Well, it turns out it gives you exactly the same information as a Poisson bracket on the dual space, because if you're asked what are the basis elements of the dual, what are the basis elements of the dual of so here G star, the confusing thing is G star is your phase space. So in other words, take G star as phase space and quantize space, and we get a unitary of G. Okay, so this is a G star's phase space with a G action. Okay, because remember that remember that G acts on the Lie algebra by the adjoint action, and so it acts on the dual of the Lie algebra by the dual of the adjoint action. So this is the co-adjoint action. So one reason that kind of mathematicians are, when they talk about quantization, one thing that they're very interested in is this problem. So there's a long history of kind of mathematicians realizing that you could, if you had some Lie group that you didn't really know what its representations were, you could look at the dual of the Lie algebra and think of that as a physical phase space for some system, and then go ask a physicist, okay, if you had a classical mechanical system with this phase space, how would you quantize it? What would the quantum theory be? And then if you can get a good answer to that, what the quantum theory would be, then you get a unitary representation of G. And it turns out that then the orbit method, it turns out that the way that G acts on Lie G star, it doesn't act transitively. It breaks it up into lots and lots of different orbits, and the different orbits of this action in this philosophy are supposed to tell you, if you pick any one of those, it should and try and quantize it, you should get an irreducible representation. So there should be some relation between orbits of coadjoint orbits of G acting on this guy and irreducible representations of the Lie group, and that's kind of the guiding philosophy of a whole industry. And it turns out that this doesn't work out as you would really like in any simple way, but it's kind of close to working out, and it gives you all sorts of inspiration about different ways to do a representation theory. So maybe you better stop there for today. And then I guess next time we'll go on to I guess, so the next thing, the next thing I think I wanted to talk about was the Euclidean group, which is a different group, and we'll start by doing a little bit of some abstract stuff about what it is, what a semi-direct product group is. But are there any questions about any of this stuff now? Yeah. Sure. Okay, well, if not, so please do. I'll shut this down, and please do kind of come back if you want to talk about anything about this or about anything else that's going on with a course, or if you have any other problems, let me know. Okay, so bye for now. Bye.
Thank you.
Bye.
Thank you. Bye.
Bye.